Everyone. Welcome back to another lesson in MCV4U. Today we'll be looking at the second derivative test to determine local extrema. So let's look at this warm-up question, and it tells us to determine the intervals of concavity and the x values for any points of inflection for the function f of x is equal to ln x squared plus 1 over 4 x to the power of 4. Here we can see that in terms of a domain restriction, we can see here again that the ln x cannot be equal to 0. And here, if we write it, we can rewrite it as f of x is equal to 2 ln x, and that's using the log laws, plus 1 over 4 x to the power of 4. So here, we'll take the derivative, so f prime of x is equal to 2, the derivative of ln x is 1 over x, plus, bring the 4 down, 4 over 4, which is 1, and x to the power of 3. Here we can rewrite it as 2x to the power of negative 1 plus x to the power of 3. Here, now let's find the second derivative, so f double prime of x, and that'll be equal, here, bring the negative 1 down, we have negative 2x to the power of negative 2, plus, bring the 3 down, 3x squared. So here we'll write it as negative 2 over x squared plus 3x squared. And here, if we put it all under a common denominator of x squared, here we will get negative 2x, sorry, so 3x squared, so 3x to the power of 4, multiplied by the x squared, minus 2 over x squared. Here we can see that f double prime of x is equal to 0 when 3x to the power of 4 minus 2 is equal to 0. So here you see that x to the power of 4 is equal to 2 over 3, and therefore x is equal to plus or minus fourth root 2 over 3. And here, so we know that again, f double prime of x is equal to 0 when x is equal to plus or minus fourth root 2 over 3. Here, for the sake of kind of understanding, again, when these values are, approximately the fourth root of 2 over 3 is 0.90. Now here, we'll draw our number line. So here we have negative infinity to positive infinity. Again, some people might choose to use a chart here. Either way is fine. So from negative infinity to negative fourth root 2 over 3, negative fourth root 2 over 3 to 0, then 0 to fourth root 2 over 3. So here, value that's less than negative fourth root 2 over 3, something like negative 1. We sub negative 1 into the equation. So 3 times negative 1 to the power of 4 minus 2. That will be positive. And then 3 and then x squared. So -1 squared will also be positive. So here, it'll give us a positive answer, which means that it will be concave up. In between -4th root 2 over 3 here and 0. So we'll pick something like -0.5. We have -0.5. So 3 times -0.5 to the power 4 minus 2. That'll give us a negative value. Then we sub in -0.5 squared. That'll give us a positive value. So here it would be the overall function would be negative. So here we see that that would be concave down. And then from 0 to 4 root 2 over 3, so sub in 0.5. We sub in 0.5, still get a negative answer in the numerator, and we'll get a positive answer in the denominator. And so here we'll see that, sorry, that is also negative, which is concave down. And finally, from 4th root 2 over 3 to positive infinity, something like 1, sub in 1, you get positive in the numerator and positive in the denominator. And so the overall function will be positive or concave up. So here you can see that therefore f of x is concave up when x is between negative infinity and is between negative infinity and -4th root 2 over 3, and also when it is between 4th root 2 over 3 and positive infinity. And then f of x is concave down when x is between -4th root 2 over 3 and 4th root 2 over 3. And then also we can say that f of x has points of inflection plus or minus when x is equal to plus or minus 4th root 2 over 3. Okay, so now let's take a look at the second derivative test. And the second derivative test determines the local extrema at point C and f of c. So let f of x be twice differentiable over an interval containing the critical number c and when f prime of c is equal to 0. So here we see that if f double prime of c is greater than 0, then f has a local minimum at x is equal to c. If f double prime of c is less than 0, then has the function has a local maximum at x is equal to c. And finally, if f double prime of c is equal to 0, then the function may have a local maximum or minimum, or it may have neither, which would be an inconclusive case. So again, to make conclusions, again, the first derivative test must also be used here. So here, example 2, it says use the second derivative test to find the x values of the local extrema for f of x is equal to 2x cubed plus 9x squared plus 12x. So here, if we take the derivative, it'll give us 6x squared plus 9x, oh sorry, plus 18x plus 12. Here we can factor out a common factor of 6. We'll be left with x squared plus 3x plus 2, which can be factored as x plus 1, x plus 2. So here we see that f prime of 0, or f prime of x is equal to 0 when x is equal to -1 and x is equal to -2. And so here, these are what we call our critical numbers. Okay, so now if we take our second derivative, so if we take our second derivative, get 12x plus 18. Here we factor out the 6 again as a common factor. We'll be left with 2x plus 3. So now what we can do is we can sub the values of, of our critical numbers into our second derivative. So here, if we sub in f double prime of -1, here we'll get 12 times -1 plus 18, and that will give us a value of 6. And so what that means is therefore that f double prime -1 is positive, which means that f of x is concave up. Okay, f of x is concave up at x is equal to -1, and that means that we have a local min at x is equal to -1. And so now we'll sub in our other critical point, which was at -2. So here we get an answer of -24 plus 18, which will give us -6. So here we see that f double prime at -2 is negative, so is negative, means that here f of x is concave up, or sorry, is concave down, and there will be a local max at x is equal to -2. Okay, so let's look at the third example here. It says determine the coordinates of any local extrema f for f of x is equal to x cubed minus 6x squared plus 5 using both the first derivative test and the second derivative test. So here we'll do the first derivative test. Okay, so here we'll derive f of x, and so f prime of x will be equal to 3x squared minus 12x. Factor out value of 3, so factor value of 3x, and we'll get x minus 4. So here we see that f prime of x is equal to 0 when x is equal to 0 and x is equal to 4. So here, if we draw our number line, negative infinity to positive infinity, So negative infinity to 0, 0 to 4. So here, if we sub in a value that is less than 0 here, so for example, negative 1, here we'll get negative times negative. And so here, negative times negative will give us a positive value. So that means that here it would be increasing. From 0 to 4, we'll sub in value such as 1. 3 times 1 is positive. 1 minus 4 is negative. So positive times negative will give us a negative value, which means that it is decreasing. And then we'll sub in a value greater than 4, so 5. 3 times 5, positive, 15. And 5 minus 4 is also positive. So here, we'll see that it is increasing from 4 to infinity. So what we can realize here is that there's an increasing and decreasing at 0 and 4. So here there will be a local max, at 0. And if we sub in 0 into our equation, we'll get we'll get 0 and 5. A local max at 0 and 5. So you sub that back into our equation of x cubed minus 6x squared plus 5. And here we see that at 4, there'll be a local minimum. And we sub in again 4 into the equation, which will give us negative 27. And so again, we're just subbing it back into the original equation. F of 4 is equal to 4 cubed minus 6 times 4 squared plus 5, which will give us negative 27. And now let's look at the second derivative test. So the second derivative test. So here, find f double prime of x is equal to 6x minus 12. And here we already know that our critical numbers are at 0 and 4. And here, if we have 6x minus 12, get f double prime 0. So we're subbing in our critical numbers that we found from our first derivative. So that's going to be equal to negative 12. And if we sub f of 4, or f double prime of 4, we'll get 6 times 4 minus 12, which will equal to 12. So here we see that, again, f double prime at 0 is negative, which means that it's concave down, and that will tell us, that there is a local max at 0 and 5, and f double prime at 4 gives us positive 12, which means that it's concave up, and therefore there's a local min at 4 and negative 27. here, again, there's just a note. Again, sometimes the second derivative test, right, is inconclusive. If so, you must use the first derivative test. So here it says f of x is equal to x minus 1 and use the second derivative test to find the local extrema. So here, if we derive this, so f prime of x is equal to 3x minus 1 squared times 1 is just 3x minus 1 squared. Our second derivative, so let's actually find, so let's find f prime of x is equal to 0. F prime of x is equal to 0 when x is equal to 1. So here our second derivative test, or our second derivative. So here, second derivative, it's 6x minus 1 times 1 is equal to 6x minus 1. So here, if we sub in f double prime of 1, which is the critical value that we found in our first derivative, we get 6, 1 minus 1, which is equal to 0. And so here, it is inconclusive what is happening here, because it's neither negative or positive. And so here we have to use the first derivative test. So say must use first derivative test. So here we'll draw our number line, negative infinity to positive infinity, and at 1. So the value that's less than 1, so 0, if we sub that in to f prime of x, that'll give us a positive value, which means that it's increasing. Sub in a value that is greater than 1. So for example, 2, sub that in, also gives us a positive value, and it's increasing, which means that here there is no local extremes.